Good morning, Math 10A class. Today we're going to learn about optimization. Optimization is finding maxima or maximums and minima. This is something that you might want to do if, for instance, you're a business and you're trying to maximize profits, or find the strategy that has the minimum costs. Maybe you're trying to work out how to travel the minimum distance to avoid some obstacle, or you're a farmer trying to maximize the area of your property. So, as a refresher, earlier we learned something called Fermat's theorem, which says that if f has a local maximum or minimum at a point C, and if f is differentiable there, then the derivative of f at C is 0. So as an example, let's say we've got some function that looks like this. Where is the derivative going to be? Where's the derivative going to be? 0. That's where the slope is flat. So it'll be at this point, at this point, and at this point. So these are all of our local maxima and minima. Now, you may have a function that's only defined over a certain interval. Here I'm defining it over the closed interval from this x-coordinate to that x-coordinate. And our textbook does not consider endpoint extrema to be local extrema. That's just a matter of definition. Other books will disagree. So these are our only local extrema. Extremum, remember, means maximum or minimum. And this one over here is our absolute maximum. And down here we have our absolute minimum, which, because of how the textbook writes its definitions, is not considered a local minimum. So how can we use that to do something that someone might care about in the real world? And for that, we're going to look at an example. A farmer is trying to create a rectangular fence for their farm, and they want to enclose the maximum area possible. And on one side of their land, they have a wall. That's going to make one side of a rectangle. So the farmer only has to build the remaining 3 walls, and they have 100 feet of fencing to work with. And they want to find the dimensions that, meaning the lengths of the remaining sides, that maximize area. Now, when I try to do a problem like this, I like to work out some examples. So one thing we could try is a fence that goes like 595. Maybe on the other extreme, towards the other extreme, we could have something like 40, 10, 40. Maybe somewhere in the middle, like, 40, 10, 40. That adds up, right? No, it does not. I'm going to say 45, 10, 40. maybe somewhere in the middle. And as a mathematician, I like to think about the ridiculous extremes that no one would ever consider sensible. So I'm going to think about versions where one of the sides has length 0, just to get the most full picture possible. And if I look at all these areas, this one has area 0, this one has area 450. And we can see sort of goes up for a bit and then goes back down. So the maximum is going to be somewhere close to this, but how can we find it exactly? Now, one of the things we like to do as mathematicians is give things names. Traditionally, we don't like to give things a name that is longer than a single letter. So we're going to let x and y be the lengths of these sides. So what do we know? We know the total length is 100, so that's x plus y plus x, or 2x plus y is 100, and we want to maximize the area, which is xy. To use the tools that we have at our disposal, it's going to be most convenient to put this into a function with only one variable. And how can we do that? We're going to, I've given away the answer, but the question is, which variable is most convenient to use? Really, you could use either one of them. I'm going to eliminate y because it's slightly easier. So I'm going to say y is 100 minus 2x. And so the area, if I think of it just in terms of x, that's x times y. X times 100 minus 2x, using that substitution. Expanding that out, that's 100x minus 2x squared. And if we want to use Fermat's theorem over here, we want to find a place where the slope, where the derivative equals 0. So how do we do that? We take the derivative and we set it to 0, right? So where does this happen? Well, we can solve 100 equals 4x, x equals 25. Is that the answer to our problem? Well, okay, let's try to draw it out. X is 25. All right, I am missing a little bit of information. I need to work out what y is, but luckily we have our formula over here for y. It's 100 minus twice x. That works out to be 50. I'm going to use units here because it's always good to have units in our final answer, and the area that we end up with is 1,200 square feet. So max dimensions are 25 feet by 50 feet, and the maximum area is 1,250 square feet. That's better than we were able to get through naive guess and check, and so I think our farmer will be pretty happy with that. And as a bonus, let's graph a of x as a function of x. So we saw that we really only care about x as it goes from 0 to 50. We can't have x be any less than 0. We can't have it be more than 50. At least not without some very strange stuff happening to this fence. And if you plug this into a graphing calculator, you'll see that it's a very nice parabola. Now, in this case, the extremum happened to be exactly between the two endpoints of the interval that we were considering. 25 is exactly between 0 and 50. This will not be the case in general, and we'll see an example of that in the next lesson.